So, hello everyone. Welcome to our December Link Tech Talk. My name is Colin Chandler, and our co-host who couldn't be with us today is me, Di. We're both LINCC Frameworks project scientists. I'm at the DRAC Institute and University of Washington, and me is at the University of Pittsburgh. The Link Tech Talks include presentations and demonstrations that showcase work done by the broader Rubin software and archives community with the goal of further enabling LSST science. And unlike traditional talks you might hear at a conference, Tech Talks highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analysis of LSST data. The Link Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. Noting that we do not have one in January. So today we have a number of speakers from our LINCC Frameworks core project, KBMOD, Kernel-based Moving Object Detection, which includes myself. We have Jeremy Cubico, who will kick us off. Please do ask questions in Zoom or in the LINCC Tech Talks channel on Slack. On Zoom, you can type questions in the chat or raise your hand. As a friendly reminder, these talks are being recorded. They will be posted on YouTube later. And it may be simplest in this case to save your questions towards the end. And with that, Jeremy, please take it away.
All right, thank you. So yeah, as Colin mentioned, we're going to be talking about KBMOD, which stands for Kernel-based Moving Object Detection. This is the aggregate work of a lot of people. The KBMOD team, both in present form and it's been an existing project for a while. So we do mention at the end the number of people who have contributed to this. So quick overview of today's talk. I'm going to start off by introducing KBMOD and shift and stack algorithms in general. Then we're going to talk about how we can change them to account for the Earth's motion, determining where we need to search, which images, how we're going to try to scale these to Rubin data, and then finish up with some discussions of data processing and results. So you'll have different speakers for each section who will introduce themselves very briefly at the beginning of this section. All right, so KBMOD is an open source software package. It was initially developed by a team at the University of Washington, has recently been jointly developed by the LINCC Frameworks team and the same group at the University of Washington. Code is publicly available, and there's been several papers written about it, starting in 2019 and 2021. I'll reference these as we talk a little bit about the algorithm going forward. The goal of KBMOD and shift and stack algorithms in general are to try to find objects which wouldn't be detectable by traditional techniques. They're too faint, they fall below the signal to noise detection. So this shows an example from the original 2019 paper where the first three images show an object which is typically brighter than we would hope to find with KBMOD. This is example that is meant to be easily visualizable. But you can see in three images, you have this object moving. And the fourth image is what happens when you center each image on the object and then co-add the images. And it really stands out. And the idea here is that the objects might not be visible in an individual image, but as we put together the evidence from multiple images, we get enough signal to actually process. The reason they're called shift and stack algorithms is we can't just stack the images. We need to account for the velocity of the object. And the idea is on the left here, we have what is actually happening if we have these aligned images. The object is moving through and passing through each image at a slightly different point because it's moving on the night sky. And if we were to take each of the images and shift them by exactly the amount the object was moving, we'd have all of the objects' locations aligned. And so if we do the shifting and then stack, the objects that are moving at that velocity jump out and are much, much more distinct. So this is a basic idea behind shift and stack algorithms. Here you can see an example from the 2021 paper where the bottom images are all thumbnails centered on the moving object. And in some of them, you can see the object reasonably clearly. In others, it's absolutely not apparent that there is an object there at all. It's within the noise. The co-added stamp is in the upper left-hand corner, and you can see we get a much clearer vision of the object. And then in the upper right-hand corner, or the kind of upper right-hand area, you see the actual time series of the light curve that comes out of each of these. And you can see we're combining evidence which is, right around the threshold at every time step, and even below the threshold, at one of the second to last time steps, it dips pretty low. But when we put it together, we get pretty good evidence. KBMOD is an algorithm that implements this, uses a slightly different looping order. And this is done mostly for implementation reasons. It actually produces the same results. But instead of trying each velocity, shifting all pixels in the image and adding them, it starts from each starting pixel and does a cone search basically out that tries each velocity. This is done because it parallelizes really well on GPU, and the implementation lends itself very well to implementing it through CUDA. But it produces the same results. We're just reversing the order in which the loops are done. At the same time, we track the best candidates seen from each starting pixel. This allows us to limit the amount of data that is returned from the core search, and to do some other basic filtering as the search goes on. There's two questions we need to answer in a general shift and stack algorithm. The first one is, how do we score the tracks? One thing we could do is just add the pixel values that we go and look for higher pixel values. The problem with this is images might not have directly comparable pixel values depending on the amount of noise and how they're processed. KBMOD uses a statistical formulation. I won't go into the details here. The 2019 paper has the full derivation and also the limitations and implications of it. But the idea is basically to ask the question, if we were to compute the maximum likelihood estimate of what the object's flux was, assuming there was an object at that pixel, what estimate do we get? And we can do this by creating two derivative images, one of which just accounts for the underlying noise, and one of which accounts for the signal and the noise at the pixel. And by just doing a simple division of the pixel values at those images, we get the maximum likelihood estimation. The advantage of this is it really allows us to combine data from different images, which might have different scales or different noise characteristics, in a single comparable way. We are dealing with the maximum likelihood flux estimate. And it also allows us to do a lot of pre-computation and then do the actual search pretty quickly. We can compute these derivative images ahead of time and then loop through the trajectories, and for each time step, predict where that trajectory is going to be, and use that to update some running sums that we ultimately use to compute the trajectory signal to noise over all of the instances. Now, the second question that we need to answer is how we actually model the trajectories. We could use a bunch of different ways of trying to predict where an object would be in a pixel. KBMOD uses a linear approach, and this balances off lower dimensionality, which means a smaller grid of total trajectories we're going to search, with the fact that objects don't actually move linearly across images, especially not when the Earth is moving and the object is moving as well. This turns out for short periods of time, or when accounting for the Earth's motion, which we'll talk about later, linear works well enough to find initial trajectories. This linear also tends to be very GPU friendly. Other approaches that we've considered involve quadratic-based projections or orbit-based projections. And these, again, you're trading off higher dimensionality for more realistic trajectories. So given the statistical formulation and the linear trajectory, we can go through the loops and compute all of these candidate trajectories and come up with a ranking, basically, of which trajectories are most likely to have pixels. Now, as I mentioned, the major problem is linear trajectories are an approximation. So I'm going to hand this off to Max, who's going to talk about recent work that we've been doing in order to improve the linearity of tracks as we account for the motion of the Earth. So Max.
Yeah, hi. I'm Max West. I'm one of the software engineers on LINCC Frameworks, and yeah, as Jeremy said, I've been working on the what we call like the reprojection, the heliocentric or barycentric reprojection problem. And as Jeremy said, we are searching through linear trajectories in pixel space, but objects don't move linearly through pixel space. These are like very slow moving objects out at the edge of the TNO range. They move very slowly. We move a lot faster than them. So they appear to us in their apparent motion to make these like nice little loop-de-loops through the sky. Really, it's us making the loop-de-loops around the sun, but we can blame the objects themselves. In a perfect world, we'd like to be able to remove a lot of that apparent motion from parallax and get a more linear view of the objects as they move through the sky. And to do this, and we can go to the next slide. We do what we call like heliocentric or barycentric reprojection. Basically, if we take a random point along the vector of our observation towards where we're observing in ICRS space, if we assume its distance from the sun, we can find this virtual point's distance from the Earth, and figure out where this would appear in ICRS space if the observation had been taken from the solar system barycenter, which will remove all of the parallax motion from the Earth because we're pretending that it's at the center of the solar system and not from the Earth. What we do is we take n randomly sampled points from our observation plane for a given image. We can do this heliocentric or barycentric correction to figure out where they would be if they had been observed from the center of the solar system. And then we can fit a new WCS from those randomly sampled points. And basically we can just take the old WCS, the old coordinate system from the image, swap it out with our new what we call EBD, or explicit barycentric correction, or explicit barycentric distance space. It's a controversial name. Andy doesn't like it. And when we sample points from the image and run them through our coordinate transformation, we will get the pixel, like the RA-index coordinate for a given pixel as if it was observed from the sun approximately. Of course, the more like exact way to do this would be to do this transformation for every single pixel in the plane. But when we actually have obviously did this in validation, when we compared just taking about 100 randomly sampled points and fitting into WCS, we're already at like sub-milli-arc second precision from taking every single pixel in an image and manually transferring that into a corrected space. So obviously, it's much more computationally tractable to just do 100 points versus millions of pixels. So yeah, next slide. So once we have our new corrected coordinates for a stack of images, we can use the unhelpfully named AstroPy reproject. So reprojection both refers to the coordinate transformation to correct for parallax space in this, but also refers to the image resampling aspect of this. In AstroPy's defense, they did take the name reproject first, so it's kind of our fault for naming it reprojection. But we can the AstroPy reproject package is really nice and fun to use. You basically can give it an array of pixel values, an original WCS, and then a new common WCS, and it will resample all the pixels in that image into this new coordinate frame. So if we have a large stack of images, all the different WCSs, we can correct them, have a single common WCS for all of them, and basically align our pixels, which allows us to search through a pixel space for trajectories. And once this is done, of course, the parallax motion is mostly removed, and we're more able to find them over longer observation baselines. Reproject also solves a lot of other problems that we're going to be running into for LSST, like rotation, which has been a problem with our current. We run on DECKM deep data, which is for the most part already is rotated in the same way for each observation and is mostly pointed at the same like stack of space every time we take an image. LSST is not. It's dithered and rotated, and they're going to be images all over the place. So we want to be able to have everything be in the same frame of reference when we're actually doing trajectory searches. And I guess I should also just count out that call out that, of course, we are doing image interpolation. It's not perfectly conserving the flexes across imagery sampling. It's kind of like physically impossible to do that when you have discrete values like pixels and are moving them between different views. So yeah, it's not perfectly exact, but we found that it doesn't really affect the results that much doing resampling this way, since we're already kind of playing a lot of games of averages anyway. Yeah, I think next slide. Yeah. So just to validate the approach for reprojection, obviously removing the Earth's parallax motion from the object is great, but of course objects don't have perfectly linear motions, even if you observe them from the solar system barycenter. That's not really how spheres or orbits work. There's still some degree of curving and arcs in the orbits as they appear on the sky. So to validate that this is actually a good approach, we have a bunch of objects observed 1 month apart, and then have both of these observations corrected, or have their orbits corrected, measured their derivation from linearity. We basically need the deviation from linearity to be less than 1 LSST pixel, because once we get above 1 pixel deviated away from linearity, it becomes much harder for us to find these objects. But as you can see, well, it's not labeled, but the yellow line represents 1 pixel linearity deviation across 1 month, which is sort of like our upper bound of time for parallax correction and search. So the vast majority of our objects fall below that yellow line, meaning that we would be able to find them searching linear trajectories after we do this reprojection over the course of a month, which is great. Okay, next slide. So if you caught, this all sounds great, but there's a major problem, which is that we don't actually know how far away these objects are from the sun. We have some guesses and we have models and simulations to test this out, but obviously our kind of goal is to find these objects. So to actually find them, we need to have a bunch of guess distances. So that's what we do. We are intelligently as possible guessing a low to large range of distances, correcting for heliocentric, or correcting for the parallax motion, and then searching through them, hopefully to find new objects. Problem is that this is very computationally expensive, both the doing the actual heliocentric corrections, but then also all the imagery sampling, which is just a lot of data. Yeah, this is I don't have like a good solution to this other than this. It's computationally expensive and kind of sucks. Next slide. And then to further create problems is that as we are doing these reprojections, you can see along the sort of bottom of this animation the distance that we are guessing from the solar system barycenter is going up. And these are sort of decam observations, stacks of decam observations, which images are lining up and could be theoretically created into an image stack to search through. They're changing and shifting every time, obviously, as we're adjusting the parallax. Things come in and out of focus. So actually going through the catalog space of all of our objects and finding out which ones would be good candidates to collect into a set of image collections and search through them is also a hard problem, and one that reprojection adds some more problems to. Luckily for me, that's not my department, so I can pass that off to Wilson, whose problem it is to actually solve this.
Hi, thank you, Max. I'm Wilson Beebe, a software engineer on LINCC Frameworks, and I'm going to discuss the sort of region search aspect of the problem that I've been working on with Colin Chandler, who's also been the one who's hosting today's talk. So as Max outlined, we've added significant computational complexity because not only do we have to, when deciding where to search, need a given time frame, need a given subset of sky to search in, we also have to consider the range of guess distances. And we basically now have the problem of we need to be able to support ingesting images and their metadata from a Rubin butler, provide some sort of strategy for figuring out amongst the reflex corrected images, how do we stack them on top of each other to maximize overlap? And we need to be able to sort of support repeatedly querying this across that range of time windows and guess distances. And we need to be very careful in our choices, maximizing overlap, because we do have sort of a bottleneck with access to GPUs. And as Max also just emphasized, reprojection and the actual resampling work is very expensive. So making the correct choices of which images are worth going through that full resampling is also important. So as just this lovely little animation here shows, we basically, as we're choosing different guess distances, so as you can see at the slide, the moving number below the x-axis is the solar system barycenter guess distance. And as that's moving, you can see how chips across these different nights that we're trying to resample together will have different overlaps. And that also affects where various synthetic objects will then fall within this chosen subset of space in the dotted green box. So next slide, please, Jeremy. So with the goal of Rubin, there are the deep drilling fields, which will have a very interesting data set for KBMOD, but most of the survey that we'll be receiving data for is what's called the Wide Fast Deep survey. And I think what's very interesting about these plots is that it shows over a randomly chosen overlapping window of like 30 days on the left and 60 days on the right, what number of visits can be stacked on top of each other. We get, for example, on the left, you can see there's very few places where we're even getting up to like 10 visits. When we're considering 60 days, we're able to construct deeper stacks of visits on top of each other. And I'm bringing this up because we want to emphasize that for using this part of Rubin data, reflex correction is definitely necessary. We need to be able to provide a way of linearizing the motion of objects across multiple nights of data to construct a high enough stack to perform a reasonable search on. So with this part of the survey, we need to be able to consider not only, we need to be able to consider long ranges of nights for which combining data in order to get a reasonable KBMOD search. Next slide, please. So part of the approach for this is that we can basically say that among a given subset of time and space that we're interested in, we can create a grid of the sky with equal patches, and then consider what would be within each patch of that sky, the maximal overlap of images that we could do a KBMOD search in. So a couple reasons why that's a good idea. For one thing, we can then make our choice about how large that patch is based on our resources available. So given the sort of fleet of GPUs we have access to and the sort of maximal memory that they have for how big of a stack of images of the size that we're choosing that we can put on to the GPU, we can choose to divide our subset of sky that we're interested in to already align with that. And then also by using this sort of RA deck aligned grid, we can more easily reason about aspects of overlap. So in this plot here, though we were discussing Rubin data, a lot of our early testing has been with deep. And here we're considering the case where we've taken 2 nights of data that are about 35 days apart. So you can see basically here's where the chips are, and on each night in actual space. And we can consider when we have divided this sky into this sort of grid of patches for this individual patch with the green dotted outline, what would the overlap be? As you can see, there's very little overlap. This has been a considerable amount of time. We don't really expect a sort of linearized trajectory. So in this case, we would have to take the coordinates of each of the chips and consider reflex correcting those coordinates, which is a lot cheaper than the full resampling of the images that Max was discussing earlier that we don't want to do. And we can consider then what choice of guess distance would allow us to have these chips actually overlap across this 35-day window and let us do a linear search for a trajectory within that stack of images. So in the deep case, with the GPUs we had available, we were able to construct patches that were 20 by 20 arc minutes in size. And that let us put stacks of were a few hundred images deep and fit all of that onto the GPU at once and doing all of that search at once. So with the deep fields, obviously, it's much smaller data than we have in LSST, much smaller view of the sky. So for this, we're only really creating 50 patches for each field that we're considering, and only really trying to answer that question of what is the maximal overlap of images for each of those 50 patches for a given field. While with LSST, of course, with the Y-fast use case, it scales up significantly to 180,000 patches. Much more complicated problem, but for now, we're just considering the deep case. Next slide, please. So as I outlined before, we can now consider for a given guess distance that when doing the reflex correction on the coordinates of those ships, we can now envision how these images would overlap when we do the full resampling. So basically, we can iterate through for each potential patch of sky that we're interested in within the overall subset of sky, and consider for different guess distances, if we're trying to resample at this guess distance, how deep of a stack will we be able to construct to perform a KBMOD search in? And I guess we can do the next slide as well. So just to sort of iterate, we're mainly considering a given time range of data and a given subset of the sky, equally subdividing that subset into the patch size of interest, and then coming up with these collections of images that will have the maximal overlap that we predict at a given guess distance and have all of the metadata that we would need to perform the KBMOD search within that patch. As I mentioned, within deep, there's like 50 patches per field. This obviously accelerates very quickly. We now have many different KBMOD searches that we'd have to consider just in that case, and deep alone, and then the problem scales up even significantly further for LSST. And to talk more about sort of the workflow orchestration and scheduling, I'll hand it off to Drew.
Hi, everybody. I'm Drew Oldag, software engineer on the LINCC Frameworks team at the University of Washington. And I'll be talking a little bit about the tooling that we've developed in order to scale everything up. One thing that struck me as I was listening to the previous talks is that what I'm going to be presenting is everything in the exact opposite order of the steps that were outlined earlier. But we're just going to go with it. So what you see here on this slide is a sort of abstracted version of the various different steps that have already been talked about. On the blue row, what you see are the various different tasks associated with what would be called a KBMOD pipeline. And on the green row are the various different intermediate files that are produced as you work through the pipeline. And one thing to note, of course, is that the output of one task becomes the input for the next. And so you have this very sequential linear, what you'd call a directed acyclic graph representation of a workflow. And the other thing that's really worth calling out here is the drastically different hardware requirements that are needed for each of the different tasks. So, some of the tasks require only a single CPU, others require a GPU, et cetera, et cetera. And so, if you don't mind giving me the next slide here, Jeremy, just like to say that in the beginning, it's quite straightforward for a single individual to run through any of these workflows by themselves if you're doing just one. But once you start to scale up beyond 1 to maybe 5 or 10, the organizational aspects of it start to become very challenging. And all of those intermediate files become difficult to organize. Requesting resources for each of those different tasks becomes a burden. There's a whole lot of babysitting that happens along the way that's required to run through these workflows. The most immediate solution to this, of course, is to just get your coworkers to help you do this so that you can all work together on it. And of course, that introduces a lovely camaraderie, but an additional set of organizational overhead that's really not beneficial and doesn't scale. So we start to look for other solutions. And the natural solution is to just write a script that will take care of this for you, run this end to end. And that again works for small scales up to 10 or maybe 20, but you quickly start to run into these issues again that you were seeing at the smaller scales of having to restart, babysitting resources, all of those sorts of things. And so we needed to look out across the landscape of other tools that were available. And fortunately, there are many tools available, workflow management or workflow orchestration tools that help us out with exactly this kind of problem. So next slide, please. We surveyed the landscape. There were tons of these to choose from. There's Conductor and Prefect and Airflow and Dagster and Pegasus and many, many more. And ultimately, we landed on one called Parcel. Parcel really addressed many of the issues that we were running into when we were trying to scale this up naturally the first time. So the first thing it does is it has a very natural integration with Slurm. So within our HPC systems, we can abstract away all the Slurm resource requests and not have to worry about those at all. It allows you to define resource requirements separately from tasks so that as your tasks slowly change or the scale of the task changes, you don't necessarily have to modify the task definition per se. You can modify the resources that are required separately from it, which allows a really nice separation. Sorry, Max, do you have a question?
No, sorry, that was
Okay, gotcha. And one of the things that Parcel does well is its ability to restart after failures. So it has a caching mechanism that allows you to zip through a given workflow up to the point where it had failed previously and then start again, so you don't waste resources rerunning tasks that already completed. And the other bit that's really nice is that it's easy to rearrange a workflow. It's treated almost like a linked list in code, such that you can move the tasks from one place to another within the workflow or insert more tasks as necessary. I would be remiss if I didn't talk about some of the downsides of Parcel as well, because there are several. Like I said, modifying a workflow is pretty straightforward, but testing it tends to not be so easy. If you want to test locally on your dev machine, you have to create a new set of resource definitions that are custom for your machine as opposed to those that are running on HPC. Unless you're planning on running on an HPC, it just becomes a bit of a headache and almost becomes easier to simply test in production just because of the nice caching and rerunability that Parcel provides. I'd also call out that logging was really quite a bit of a headache with Parcel. A lot of bespoke code was written in order to organize the log files so that we can keep them organized and keep them in an understandable state. I think the biggest aspect of Parcel in any workflow orchestration system that's worth calling out here is the dichotomy between the mental mapping of the workflow as compared to what actually gets implemented and run on a particular system. The mental mapping is quite linear and quite straightforward, and you can see them in very distinct steps. But to maximize the efficiency on a given system, for instance, in this case, what we ended up doing is for the first two columns, the hydrate work unit and reproject, we had to merge those two tasks together because the disk I/O operation for writing out a work unit and reading that back in was such a bottleneck that it was really a big hit to the efficiency of the system. And so as you tune to a particular system, what you end up with is a much more bespoke workflow that maybe isn't as portable to a new system in the future. And so there's some sort of balance that you have to acquire if you want portability or if you want maximum efficiency on a system. So anyway, to end on a high note, the best aspects of Parcel: excellent caching, restartability, workflow management stuff. The thing that it provided more than anything else was its ability to scale up. And so instead of us limiting ourselves to only 10 or 20 workflows that we could run at a time, we could literally run dozens or hundreds. And to talk a little bit more about the data processing side and what was involved in that, I would like to hand this off to Dino.
Thanks. Can everybody hear me? Can you just get a thumbs up to check? Perfect. I'm going to have to brush it a little bit. I apologize for that. But like Drew said, I want to tell you a little bit about what it looks like when you apply it in a data set. Then obviously we want to run a Rubin. We've been talking about Rubin, but Rubin doesn't have data yet, right? So we picked DECA, Ecliptic Exploration Project, or Deep Survey, because the data sets are kind of similar, right? They're similar in data volume. They're similar in the single exposure limiting magnitude. In terms of cadence, Deep kind of looks like Rubin DDF, and historically we have processed Deep before with KBMOD, so we have some results to compare with. Next slide, please. Fundamentally, Deep is a could you just play the YouTube video on repeat? Fundamentally, Deep is a multi-year targeted survey, right? So that's what's shown on the images on the right. For each of the stair, the goal is that the survey will do 3 pointings in each year in different colors here. So in the first year, they visit the 3 black ones. Second years, they hit the blue ones, revisit the black ones. In the third year, they hit the red ones, revisit the blues, or visit the blacks, and so on and so on. Right, and then they specifically target the standout region around the ecliptic because it's a survey designed to find KBOs and TNOs, right? And that's a pretty good cadence for KBMOD and opens 2 different search strategies we could use. One you already heard about,
earlier, and the other one is where you can just do per night, per CCD kind of searches. And these are really good because this survey has a pretty dense sampling and observation within a single night. So when you do it per night, you have many collections that have hundreds or more images. All the objects at all distances, their trajectories will remain very linear. You have more data to process, you cover more of the sky, so you increase your chances of finding something. Or as if on the right, if you're starting to reproject this at all different kind of guess distances, you can see how you have this effect of basically folding the fan back on itself. So for each of these overlapping little histogram bins, you have many, many more observations per that bin than you have if you do the survey per night, but you're searching a smaller area in the sky, and the object trajectories will only be linearized for the objects that are very near the guess distance. Yeah? All right, so what we're going to talk about is this first, very wide, very happy search across everything. So to get there, obviously, we want to reprocess the data with the Rubin science pipelines because we want to test our integrations with Rubin because we're prepping for Rubin. So what that looks like is you sit down, you download the deep survey raw data from NoirLab, then you use the Rubin batch processing system to schedule and manage your processing. That's really just a balanced output for Slurm again on Clone, which is our compute resource. The benefit of this is that it takes the internal abstractions from Rubin and then translate it into executable Slurm scripts for us. So we don't have to do that bit, but what we do have to do is write a pipeline, right? And the general outline of our pipeline is that you do instrument signature removal, that's dark slide biases, bad pixel mask, and so on. You do calibration and characterization in terms of Rubin, which is basically just photometry and astrometry. Then you resample all of these calibrated exposures onto a common pixel grid. You co-add them, that provides this super high signal to noise ratio images that you can use to derive templates to then subtract back from the original images. And what you get is what you see on the next slide, please. A set of like these three images. And of course, it's a lot better, you know, to search the image on the right, the difference exposure, which ideally would have no stationary object in it, but always there's residuals. You can't avoid it. It's still a lot better than confusing KBMOD at all of the potential sources in the middle image, right? To do this execution, there's a lot that has to go into it. You have to have a really good knowledge of Rubin. You have to have a really good knowledge of all of the calibration data products that they use and they produce to get a good result. It's not a trivial matter to write, and it's quite a lot of work. One thing that was really painful here is that log management tool, workflow, and campaign tracking tools were all very poor. In the build we use Thero, their official verification validation framework is not really quite well fleshed out. So we had to ship a lot of our own stuff, right? And what I want to impart on you, if you go to the next slide, that organization here is key, right? Rubin uses these things called collections to kind of group data, at least in the abstract within the butler itself. They can have an arbitrary name. So very early on, we came with this very complicated template that we use to name our campaigns. That includes stuff like, you know, data processing, which stair, which field, what was the date of observation, etc. And it's technically not necessary to do this, but I want to point it out that it was a very practical thing to do because you don't know all of the failure cases of a software as big as Rubin. So figuring out very quickly and being able to iterate on data reprocessing was very, very helpful, right? Of course, if you go to the next slide, we also do a lot of log parsing. There's so many logs, and they're very big and very detailed that Rubin puts out. So we have a package that takes these logs, parses them into SQL Alchemy model, puts them in a Postgres database on Epic. We have an analysis notebook, and as we're processing, we're constantly updating these results. And then, let's say, for example, top right, you can see immediately, right? CCD2, 31, and 61 are bad. That's not a surprise for anybody that knows KBMOD, but let's say on the bottom plot, you can see which nights were bad or had bad weather. And this was a really, really, really useful tool for us, right? If you go to the next slide, you'll see that HTML table of all of the logs per run per task. You can click through all the way down to the raw logs. This was only partially useful. It was very useful at start when we we're trying to learn what the failure rates were, but then it wasn't that useful in the end. I will skip some of this, but I would just like to mention that if you notice, there's a lot of different flags we assign to the object because in a distributed large-scale processing system, there's a lot of different failure cases a job can have. Some of them are recoverable, some of them are not. Figuring out what's happening is quite difficult. In the end, you'll just end up dividing these completion tables. If you can jump to the next slide, please. Yes. And then you just keep iterating on the broken stuff, changing the processing parameters, changing the processing, the way you're processing stuff until you get a satisfactory completion rate, right? So alongside all of this work is a benefit. And the benefit is that you get to characterize a lot of things in your data, right? Like if you jump on the next slide, what we do is we insert a lot of fake objects into our raw data sets. Basically kind of like a uniform distribution of fake name-built objects and fake TNO objects. And the purpose of these is ultimately to find how many of these we recover with KBMOD and get like a completeness ratio out of it, right? But they also let us characterize other effects that you don't necessarily expect. Like on the next slide, you have this problem of which statistics you pick to create your QRAD templates and which data you pick to create your QRAD templates. And that's basically what these pictures are showing. In the first row are the calibrated exposures, cutouts around a very bright fake object. In the second row is the QRAD template. In the bottom row is the difference between the first and the second row. And you can see that because the survey cadence of deep is such so dense in a night, and then you don't exactly revisit the same field, you always kind of end up with the signal from the object in your QRAD, and that creates this trough through which your object moves, and it doesn't have a symmetrical PSF anymore, and so on and so forth, right? So if you do force photometry measurements for a set of these, on the next slide, you can see which coaddition statistics works best for you, right? And for us, the blue line here is the calibrated exposure measurement of the flux of these objects, of the fakes that we inserted, and you can see that if you just use all of the data and you add them as a median, that's when we get the least tail end of the last flux there in minus 200, the green line, right? All right. So now you get, so this is kind of the story. If you jump to the next slide of like, okay, so you verified your data, you've processed your data, you verified the completion of the processing is good enough, you validated some kind of science measurements on it, and now you get to the point where you can run KBMOD, right? I don't want to bore you too much with it because we're running out of time. You do more of the same, take stock of your resources, take stock of your data, and start processing, right? Do your logging right, be organized. And in about 2 weeks, we did majority of this work, every collection with 39 images or above, using about 40 to 1,000 GPUs. Next slide. The log parsing and stuff is a lot easier. I just make these really big Gantt charts of all of the tasks. Failure cases are a lot less numerable than in Rubin, so it's easier to figure out which ones are bad. We're gonna skip a little bit ahead, only a few % failed, so next slide. And then you get to the fun bit, right? As you're processing, you also want to try to keep track of your science quality, right? We insert a lot of fakes. A lot of these fakes are dimmer than 28 magnitude. That's on purpose. But that also means that even in a 100 image stack, you'll be past the limiting magnitude you can see. So as you're processing, you want to make like a cut on the brighter end of the objects, and that's what the top plot is showing you. The blues are all of the inserted fakes. The orange is all of the recovered fakes. And you can see that generally we're doing really well. There's a few nights that just seemingly have no fakes inserted in them, which is a problem with the fakes. And there's a few nights that just have an abysmal recovery rate, which is generally a problem with bad weather and bad images, right? We are surprised, I'm surprised that the trend with PSF full width half maximum, with sky background counts, or with sky nodes are not as strong as I would expect them to be. There is a trend, but it's kind of a mystery why it isn't stronger, right? Okay, but ultimately what you want to answer is the question of all possible detectable fake objects we put in, what percentage bin per object property like magnitude did we recover? And that's basically what the next slide is showing you. Skip this in the interest of time. That's what basically this slide is showing you. In blue, per night, per stair, the recovery rate. In red, across the entire survey. And the dots, the red dots are bin recovery rates and not the fitted logistic function. The vertical line is limiting magnitude of 25.51, at which we achieve 50% recovery rate across the entire survey. You can see that we're doing really good, especially on the bright end. Limiting magnitude of deep is about 23.5 or something. Our total limiting magnitude is about 2 magnitudes deeper than that, so that's also pretty good. I think interesting bits that people will notice is low recovery rates on the very bright end. I think that's a problem with the processing. We need to reprocess the data. And then a jump again in the recovery rates at the very dim end. And that's because I think we do positional cross-matching between these catalogs. And it's very difficult sometimes for very close, compact binary fake TNOs you put in to figure out, are you landing on the primary object or on the secondary object? And I think that's why we have that little spike in the completion rate on that side. The right-hand side, it's the same plot. The gradient is that red line, same cutting off magnitude. You just plot it in terms of rate of motion and magnitude, where you bin per night some kind of an average magnitude for each object and some kind of an average rate of motion for each object. The white dots, that's the black dots. The white dots is what we directly recover. The orange dots is what we do not directly recover, but belongs to the orbit of the same object, right? And overall, we do really good. If you jump to the next slide, will be my final. We do 7 times as more data at the same time. We search twice the size of the parameter space that the original search did. We have higher right-hand completion. We have a very comparable M50 limiting magnitude. Especially if you just compare B1 to B1 and not across the whole survey, because B1 has the best data. We have a lot more tools in the pipeline. We have a machine learning algorithm that cuts our results from 400,000 to like 70,000. We got stamp fees and stuff. We have force photometry scripts. And we are in a really good place to actually tackle Rubin data as it starts coming down the pipeline, is generally my conclusion. Everything seems to work just fine. I'm gonna hand it over to questions now. I apologize for the slight delay in time.
All right, I think as Dina said, we are ready to open up for questions. Again, I want to point out that this KBMOD is the culmination of a lot of work from a lot of scientists. So, thank you to everybody who's worked on it, past, present, and in the future as well. All right, questions?
And feel free to raise your hand here or ask in the Slack channel or in chat. I think, well, we give folks a second to scramble, and it's totally loaded for me to ask a question, but I'm going to do it anyway. Max, actually, this is a question for you, and I think you answered this, but I think some people might want to know is, does this reproject that we're doing for the images, does it also handle this sort of arbitrary rotation that LSST is going to provide us?
Yes, or more specifically, AstroPy reprojects will handle that. And as long as we are selecting for the same WCS in whatever co-rotated space for all of the image stack, yeah, it'll resample it and rotate the pixels.
Awesome, great. We've got a question from Gary, which I'll read out. And that is, what is the goal for the closest source distance that will be searched comprehensively each month? Using how many full-time equivalent GPUs will that take? I see. So you're asking about the reprojecting distances and what we're planning on doing. We are still actually testing which reprojection distances we're going to work with. I think we pretty much set an inner limit at 30 AU at this point. But Dino, if you'd like to speak more to that, go for it.
Yeah, yeah, sort of. It depends also now on the cadence for LSST, which is also somewhat changing. If the amount of data you have is low, we will do a lot more distance guesses, I would assume. But they're transitioning from the 2 snapshot to 1 32nd exposure, and that changes the counts on the sky for us a little bit. So we need to rework some of those histograms. Full-time equivalent GPUs that will take.
20 terabytes of data is about the size of the image differences for the entirety of deep. I think we can do that in about 10 days. It's difficult to estimate the full time. If you go back a little bit into the estimation there, more, right down, no, down, yes. The best case scenario is, 3,500 hours worth to do everything from deep, and that's about 20 terabytes. Took us I think I can squeeze it into 10 days on about 40 to 100 GPUs. It's not impossible. Certainly, at some point, like the amount of data from Rubin is too big to keep track of. So choices will be made.
Great. All right. Gary says thanks. Any other last quick question? I think in the interest of staying on time, we should probably call it right there. Thanks again.
Question.
Go ahead.
Loretta, did you lift your hand just a sec? So, all good.
All right, great. Awesome. Well, thanks again, Jeremy, and everyone else who spoke today. And thanks to everyone for attending the Link Tech Talk series. We have a brief hiatus in January, and we will return for the next Tech Talk on February 13th, 2025 at 10 a.m. Pacific. We're going to be hearing about AI multimodal spectral matching from Francois Lanus of the French National Center for Scientific Research, or CNRS. If you haven't already, please join the LSST #Link Tech Talks channel on Slack. There's the link at lists.lsst.org mailing list for announcements and more information. There's information including links to the Rubin Community Forum and the calendar on the LSST Discovery Alliance website. And we will be posting this talk on YouTube within the next few days. And with that, thanks again, everybody, for joining us. Have a great rest of your day or night.